And yes, I'm going to talk about the Hamiltonian flows on the Hitchin component and what kind of interesting consequences they can derive from these Hamiltonian flows. And today I'm going to talk about the background and how we define these Hamiltonian flows and some properties of them. And tomorrow I'm going to attack actual applications. Yes, let me begin with the very basic stuff. It's Teichmuller spaces, where actually everything got started. So it's better to know something, some motivation and historical kind of thing before we actually start with. So let's our setting is as follows. So S is always a closed orientable surface of genus at least 2. In this setting, our surface S always supports a hyperbolic metric. What I mean by hyperbolic metric is a Riemannian metric with a sectional curvature constant -1. And the Teichmuller space of S is morally just to collect all the hyperbolic metrics defined on S, and you take the equivalence class. And the equivalence class is defined as follows. So the hyperbolic metric G0 and G1 are equivalent if and only if there exists a one-parameter family of self-diffeomorphism f of t that brings one metric G1 to G0, and this identity at time 0. So basically, you just like have a metric, and two metrics are equivalent if you can go one to the other by just like continuously deforming one to the other. So this is a very like philosophical definition. It's a nice definition, but it's kind of giant space modeled by giant space. So it's not very practical. So we have to kind of better to have some smaller space quotient by smaller subspaces. That's something they can do by using our famous uniformization theorem. The uniformization theorem tells us that the universal cover of your hyperbolic surface is always isometric to the standard one. Standard one is the upper space, upper plane with a very fixed hyperbolic metric. So that's the uniformization. If I have a uniformization, then we can do the following game. So suppose that you are given a surface with a hyperbolic metric. And our uniformization theorem tells us that there exists an isometry between the universal cover with the lifted metric to the upper plane model. And your fundamental group of S can be identified with the deck transformation group. And this deck transformation group acts on your universal cover as an isometry. And we define the following representation. So it just, if you have a deck transformation group element, we just take the conjugation by this isometry. Then you get, because everything is isometry, you get the image in the isometry group of hyperbolic plane, which is as a regroup, this is isomorphic to PSL2R. And this particular representation is called the holonomy representation, and secretly this isometry is called the developing map. So this is so we do this construction for a given fixed hyperbolic metric, but our Teichmuller space is a equivalence class of hyperbolic metrics. So we have to see what happens to this holonomy representation and developing map if we have a equivalent hyperbolic metric. So suppose that we have a two equivalent hyperbolic metric. What does that mean? We have a one-parameter family of diffeomorphism. At time t is an identity, and time 1 is an isometry between these two. So then we have two isometries between two universal covers that identifies these two with a standard model. And you also have two holonomy representations. And also we can lift our one-parameter family diffeomorphism to the universal cover. So we have a one-parameter family of diffeomorphism on the universal cover, and you consider this map. And what we can observe is that, well, at time 0, where this is an identity map, so we have K naught equals this isometry. And time t, we have something, but at time t, we can see that the pullback of G naught is G1. So basically, at time t, this K1 is another isometry from S Twitter, G1 Twitter to the standard model. And if we have two such a isometry, they must be differ by the post composition by the isometry group of H2. So we have this relation. And this is a little bit subtle, but for any t, their action on the ideal boundary of H2 is the identity. That's because this HT, because, S is the closed surface, and if you lift Ft to the universal cover, this has an effect on the fundamental domain, which is completely contained in your interior of our H2. So it doesn't really perturb your boundary. So that's why we have this relation. So at time 1, particularly, we have this. And let's see what happens to our holonomial representation. So by definition, your holonomial representation can be written as this. But if you restrict yourself on the ideal boundary, by using this relation, we can write it down as this. And this is nothing but the conjugation of your first holonomial representation by our isometry K. So this is true for this. This is true on your ideal boundary, and because PSL2 action on the boundary completely determines its action on H2. So the holonomy of the first metric is conjugate of the holonomy of the second metric. The upshot is, given any Teichmuller space element, you can associate a representation of your fundamental group into the isometry group of H2, which is PSL2R, and the equivalent, and if you take the conjugation by this PSL2R, we have a well-defined map from Teichmuller space to this so-called character variety. Okay, so this space is much more concrete than our original definition. And in fact, this holonomy map is injective. That's what you have to show, but I'm not going to talk about it in this moment. Okay, so of course, we can achieve every representation by using this holonomy map. And you can observe that the image of this holonomy map is precisely the set of all discrete and faithful representations. Therefore, we have a one-to-one and onto map from the Teichmuller space into the set of all discrete faithful representation modeled out by PGL2R. I secretly use PGL2R instead of PSL2R because there is an ambiguity coming from the orientation problem. So if we take the quotient by PGL2R, we identifies two identical kind of Teichmuller space. So we have a one kind of well-defined Teichmuller space here. And we can also see that the Teichmuller space is a full connected component of this character variety. And as I mentioned here, this component consists solely of discrete and faithful representation. So this is so in some sense, Teichmuller space is a very special connected component in this character variety. And what I'm going to do is to upgrade this classical Teichmuller space to a higher Teichmuller space. So what I mean by higher, we have a higher rank Lie group here. Previously, we have a PSL2R Lie group here, and it has a rank 1. And now we consider the semi-simple real Lie group of rank at least 2, then it becomes higher. So the higher Teichmuller space, if there exists, is a union of connected components of this character variety that solely consists of conjugation classes of discrete and faithful representations. It may exist or may not exist, but the theorem by Hitchin, Labori, and Guichard, and Foucault-Goncharov, what they showed is that, so suppose that we are given a Lie group G, which is a split real form of a simple complex adjoint group. Then so-called G-Hitchin components are Teichmuller spaces, or are all higher Teichmuller spaces. Where if you are allergic to, for example, me, if you are allergic to these like complicated terminologies, you just assume that G is like PSL N R, which is AN type, PSO N plus 1 N, BN type. I messed up the order. PSO NN, this is a DN type, or real symplectic group of rank 2n, this is a CN type. Or there are many like exceptional Lie groups, but you just imagine that G is one of these classical Lie group, concrete classical Lie groups. If your G is this, we have a higher Teichmuller space, which is called the Hitchin component. So this is kind of motivation to study like Hitchin component. And next slide, I want to define what these G-Hitchin components are. To do this, we need some preparation. So suppose that, this is a kind of theorem. You can always find a triple EF and H in your Lie algebra of G that satisfies these kind of relations. And also we can find the EF and H as a regular elements, whatever it means. And if you can find those elements in your Lie algebra, then you can find you can construct the following diagram. So this is a relation that's satisfied by SL2R Lie algebra. So once we have this, we have an isomorphism from SL2C into the complexification of your Lie algebra. And this Lie algebra embedding can be integrated to Lie group embedding of PSL2C into your complexified Lie group. This can be done because our SL2C Lie group is simply connected. And you collect all the real points of this Lie group. Then you have this, and you do the same thing on this. Then you have our original Lie group G, and we have a restricted isomer embedding here. And because G is a adjoint type, this map factors through the PSL2R Lie group, and induced map from PSL2R to G will be denoted by tau of G. And this is the preferred representation of PSL2R into our Lie group G. And in some sense, this is kind of unique up to conjugation. So this is really the preferred one. So for example, if your Lie group G is given by PSL3R, we can find a concrete embedding. So we just send this element to this kind of elements. So here's the definition of Hitchin component and Hitchin representation. So G is our Lie group that satisfies these conditions. And then representation law from your fundamental group of surface into G is G-Hitchin representation if there exists a one parameter family of representations such that at time 0 it is our original representation, and time 1 is the representation is of the form of this. So tau of G is the preferred one that I constructed before, and law of F is a discrete faithful representation, or it's another name for like Fuchsian representation. So this is a G-Hitchin representation is nothing but a representation that contained in the copy of Fuchsian representation. So we collect all this G-Hitchin representation and denote it by Hitchin with bar. And if you take the conjugation class, we just write it as Hitchin of G of S. So let me tell you some properties of Hitchin representation and Hitchin component. Well, this is the higher Teichmuller space. So this is something that I'm repeating. Like every element in every Hitchin representation are discrete and faithful. Topologically, G-Hitchin component is diffeomorphic to the cell of certain dimension. This is a classical result by Hitchin. And compared to the classical Teichmuller space, well, Teichmuller space is diffeomorphic to R to the 6G minus 6, where G is the genus of your surface. And well, PSL 2R is dimension 3. So if we put 3 here, they match each other. And the mapping class group acts on your Hitchin component properly discontinuously, and the action is given by this rule. So if you have a mapping class group, and if you have a Hitchin component element, and we just pre-compose it with the inverse, induced map on your fundamental group, and take the inverse, pre-compose it, and take the conjugation class. That's the action of your mapping class group on your Hitchin component, and this action is properly discontinuous. And this is a result of Labori. Therefore, we can construct so-called Hitchin Riemann moduli space by taking the quotient of your Hitchin component by the mapping class group. This is a Hausdorff space, but usually it's not a manifold. It's an obifold. And there is a mapping class group action invariant symplectic form, so-called Atiyah-Bott-Goldman symplectic form. And there are Riemannian metric that is invariant under the mapping class group action. So this is a result of Goldman. And this part is a result of Bridgman, Canary, Labori, and Zambarino. And in the Teichmuller space, we have a Beyer-Patterson metric and Beyer-Patterson symplectic form. And they are generalizing these two objects. And you have a symplectic structure, so you may ask whether this Hitchin component is symplectically trivial. And this is actually the case when G is equal to PSL NR. And this is a result of Sun Winard and Jang. And when n equals 3 particularly is a result of Choi, myself, and Hongchan Kim. And they are all classical kind of things. And now I want to add 2 more properties on it. So first thing that I want to mention, this is one of our main theorem, is the work with Seoyoung Choi. Let's say G is a PSL n plus 1R, PSO n plus 1n, or PSP 2nr with n bigger or equal to 2. And then the total volume of total Atiyah-Bott-Goldman volume of the moduli space is always infinite. Here's the comparison. In the classical Riemann moduli space, they're not Atiyah-Bott-Goldman, but Beyer-Patterson total volume is always finite. So this result shows that mostly higher Teichmuller spaces and classical Teichmuller space are kind of the same, but in terms of the mapping class group action, they are completely different. That's something that this theorem tells us. And the next theorem that I want to mention is something related to the strong denseness of representation. So representation is strongly dense if, okay, say we choose we pick 2 elements in the fundamental group, and evaluate these 2 elements by the representation. Well, these 2 rho of x and rho of y may generate or may not generate a Zariski dense subgroup of G. If it happens to generate Zariski dense subgroup for any choice of non-commuting x and y, then you call this representation strongly dense. And our main theorem shows that G-Hitchin representation are generically strongly dense. That means away from codimension 1 analytic subvariety, these Hitchin representation are always strongly dense. And this is a kind of generalization of Long-Reed and Wolf. They prove that PSL and R Hitchin representation are generically dense. As a comparison, well, Fuchsian representation are always strongly dense. So we don't have always list, but generically they are strongly dense. Okay, that's the 2 theorem that I want to mention. And these 2 look very different, but the proof of these 2 theorems use the same idea from this Hamiltonian flow, so-called Goldman flow. This is very special types of Hamiltonian flow, specially defined on Hitchin component. And yes, the proof of these two theorems use this technique of Goldman flows. So that's why we have to study Goldman flow today. Okay, do you have any questions so far? Otherwise, we can move on to the Goldman flows, this definition. So before I define the Goldman flows, I have to mention this symplectic form, Atiyah-Bott-Goldman symplectic form, because I said Goldman flow is a Hamiltonian flow, and Hamiltonian flow, you have to know what symplectic form you are talking about. So let's define Atiyah-Bott-Goldman symplectic structure. So this is kind of classical result. So basically tells you that the tangent space at certain point of your Hitchin component can be identified with the first cohomology group of your fundamental group with a twisted coefficient. And this twisted coefficient is nothing but, as a vector space, it's just the Lie algebra of G. And the action of the fundamental group is given by the adjoint action defined as follows. So this is kind of classical result. And the Atiyah-Bott-Goldman symplectic form first can be defined at each tangent space. So we first choose a symmetric bilinear adjoint invariant non-degenerate form B on G. For example, you can choose the Killing form, but you can also choose a trace form. That is much easier. But all of them are kind of whatever this kind of thing you choose, they are all same up to constant multiple. So it doesn't really matter which symplectic bilinear adjoint invariant non-degenerate form you use. So you choose one, and then the Atiyah-Bott-Goldman symplectic form is defined pointwisely by the following map. So we have a product of tangent spaces, and you take the cup product. This is a very usual cup product, and you'll end up with the second cohomology group with this tensored coefficient, and you apply this B, and then you have a class in the usual second cohomology group, and you take the Poincare dual of it, and we end up with some real number. And the composition of this series of maps is the value of the Atiyah-Bott-Goldman symplectic form at this tangent space. And by construction, you can easily see that the Atiyah-Bott-Goldman symplectic form is skew-symmetric and non-degenerate. What you need to show is that it is actually closed two-form. So this shows that, well, this is a two-form, non-degenerate two-form, but to be this non-degenerate two-form be a symplectic form, you need to show that this is closed. And this is really kind of hard, non-trivial part. And Goldman, Weinstein, and Hoboshiman, and many other mathematicians are involved in proving this fact. So, but we have this. This is what I mean by Atiyah-Bott-Goldman symplectic form. And now we defined the Goldman flows. So setting is follows. So we choose a oriented essential simple closed curve on S, and you choose an element in the Cartan subalgebra is fractals A of your Lie algebra of G. And let's say A plus be a positive Weyl chamber. Well, I use very fancy word, but this is nothing but, for example, when G is a PSL NR, this is nothing but the set of, this Cartan subalgebra is nothing but the set of all diagonal matrices with the zero trace. And the positive Weyl chamber is a subset of our Cartan subalgebra satisfying this condition. So it's basically a set of all diagonal matrices with zero trace, and their diagonal entries are kind of all distinct and it's sorted according to their size. So you don't need to know what these Cartan subalgebras are, but the property that we need is that any two elements in the Cartan subalgebra commute each other. And the importance of this Cartan subalgebra is that this is the theorem of Labori and Fock-Goncharov, and they proved that for any Hitchin representation and for any non-trivial element in your fundamental group, the law of X is always purely loxodromic. That means this element is always conjugate into this positive file chamber. That's the theorem of Labori and Fock-Goncharov. Now we can define our Goldman flow. So our setting, just remember, like gamma was a oriented essential simple closed curve, and Q was an element in the Cartan subalgebra. And suppose your gamma is separating, meaning that if you remove gamma from your surface, you get a two connected component subsurfaces. And you choose a base point P in your gamma. So pictorially it looks like this. We have a surface, giant big surface, S, and you have a gamma here oriented as follows. And because the gamma is oriented, we can say, we can define the left-hand side and right-hand side and choose P here. And then by using Van Kampen theorem, you can decompose your fundamental group as an amalgamated product of the fundamental groups of left subsurface and right subsurfaces. And let's let rho be a Hitchin component, Hitchin representation. And as I mentioned, rho of gamma is conjugate into the positive Weil chamber. So why don't you just take a representation such that rho of gamma is actually in the positive Weil chamber, not just conjugate into it, but just say this is inside by taking suitable conjugation. Just assume that rho of gamma is in the positive Weil chamber. And then we define the following new representation as follows. So this your fundamental group is decomposed as a amalgamated product. So in order to define a new representation, you just tells you how your kind of what is that how your generator goes and this map satisfies this amalgam, this extra like what is that extra relations. So you just send the element from the left subsurface to as it is, and send the right hand side subsurface to a conjugate of conjugate by T of Q. And you can check that this map satisfies this condition because everything is commutative, and rho already satisfies. You can just cancel them out because everything is commutative. So this gives you a well-defined representation of your whole of pi1 of S into G. So, and then if your gamma is non-separating, we choose a simple closed loop alpha that intersect once with your curve gamma, and choose a base point in the intersection point. And pictorially it looks like this. So you have a surface and non-separating curve gamma, and the alpha is here, and you choose a base point here. And then your surface group pi1 of S can be written as a HNN extension, meaning that you have all this pi1 of S naught, which is the subsurface of this, and you have an extra generator alpha that plays a role of this extra transverse curve, and this alpha satisfies this following extra relation. And to define a new representation, we just specify where this element to be mapped. For example, if your x is coming from the original subsurface, you just do nothing. And if your x is the extra generator, we send it to the row of alpha multiplied by exponential of minus t of q. And you can check that this map satisfies this map respects the extra HNN relation. So this extends to the representation of pi 1 of S into G. Right, the Goldman flow now can be defined as follows. So the Hitchin component is the conjugation class of representation. So pick an element in the Hitchin component and you lift it to the actual representation that satisfies this condition. And then we play our game, this f of t, f of bar, and then you take the conjugation class. Then this will give you a well-defined flow in the sense that it doesn't depend on any choices that we have made to define it. For example, it doesn't depend on the isotopic class of gamma. And it doesn't depend on the choice of rho prime, provided this rho prime satisfies this condition. So this gives you a well-defined flow, and we call it the Goldman flow along gamma, and in the direction of Q. Okay, this is our definition for the Goldman flow. So if you have any question, please, this is good time to ask a question. Otherwise, we can move on to the some properties of Goldman flows. Okay. So I defined the Goldman flow, and I secretly said that this Goldman flow is a Hamiltonian flow. So whenever I say Hamiltonian flows, I have to say that, okay, what is the Hamiltonian function associated to it? So that's kind of what I'm going to do. So I'm going to define the associated Hamiltonian function to this Goldman flow. So let U be the set of all purely loxodromic elements in G. And you say that the function, differentiable function, f defined on U to G is an invariant function if it is differentiable and it is invariant under the conjugation. And given an element in your fundamental group, define f of x to be a real valued function by this rule. So f of x of rho is just the f of rho prime of x, where rho prime is in the conjugation class of rho. This is a well-defined map because our f is invariant under the conjugation. So this is a well-defined map on your well-defined differentiable real valued map on your defined on your Hitchin component. And for each x in G, there is a unique element in the Lie algebra satisfying the following condition. So what is it? It's just move slightly from your point x and take the first derivative. And because B was a non-degenerate symmetric form, we can always find find an element that satisfies this condition for all y. And this function that associates an element to the real algebra element that satisfies this relation is called the Goldman function of F. Yes, please. Yes. Oh, I'm sorry. This is a mistake. This should be R. Yes. Sorry. Yes. Thank you. This is R. Yeah. And we call this Goldman function. And now we can we compute this Goldman function for particular class of invariant functions. So U, as before, is a set of all purely loxodromic elements. And say lambda is the Jordan projection. Is the Jordan projection. This is nothing but the taking kind of the eigenvalues of your element. If G is a PSL NR, it's just nothing but the taking the eigenvalues. And you pick any element in the functional of your Cartan subalgebra, and you consider this following map. And this is invariant under the conjugation because lambda is invariant under conjugation. And the lemma says that, and we are going to use this as a Goldman, this as an invariant function. But to say this, well, we need to know that this function is at least differentiable. Well, alpha is already differentiable, so the important point is that this Jordan projection is differentiable. I think this is kind of known to experts, but I can't find any reference that states explicitly saying that Jordan projection is differentiable. So I just added as a lemma. So U is an open set. This is also kind of well-known fact. And you can show that alpha composite with Jordan projection is a real analytic. And this is much stronger than just saying this is a differentiable function. And in fact, this is a real analytic. And for an element in the positive Weil chamber, the Goldman function of this particular invariant function is just a dual of alpha. So it's the constant function on the Weil chamber. Where what I mean by dual is the element in the Cartan subalgebra that satisfies this condition. You can find such a thing because our B is a non-degenerate symmetric bilinear form. Okay. So the first two facts actually come from the fact that the distinct eigenvalues varies analytically. This is kind of classically known fact. And because our regroup G is kind of abstract object, not just a PSL NR or something. This is not actually a proof, but the actual proof is almost the same as this fact. So I just say, well, because these eigenvalues varies analytically, we have the analyticity of this function. So we only have to show this fact. So let's say f is our invariant function. Let's say x is the exponential of some element in the positive Weil chamber. And this Baker-Campbell-Hausdorff formula tells us that the logarithm of this multiplication can be written as follows. So up to the first order, we have something and the high order terms. And you also have something called the restrict root decomposition. So you can decompose any element can be decomposed into element in the Cartan subalgebra and some restrict root vectors. And the restrict root vectors satisfy this condition. So you just apply this decomposition into here. Then you get this. So we just have this eigenvalues instead of adjoint action. And you have a high order term. And you just compress this part as Z. And then you can find an analytic path that passes through the identity element. That's by taking the conjugation, we can take this element into the positive Weyl chamber, because for a small enough t, this element is purely loxodromic, so you can always find those analytic curve. And because of this curve is analytic, you can expand it. It's a Taylor expansion. And we don't have the constant term because g of naught at time t, this is the identity. So we don't have a constant term here and the higher order term. And you just evaluate this expansion. And then we have this. And this means, so this conjugation sits inside the positive Weyl chamber means that of the first order, this whole gadget must be inside the positive Weyl chamber. And you can observe that if you do the restricted root decomposition of this element, it doesn't have any Cartan subalgebra factor. And Z also doesn't have any Cartan subalgebra factor. So in order to this hold, we must have that the sum of these two elements must be 0. So we have this. So actually, we don't have this part. And then if you take the Jordan decomposition, we only have up to first order, we only have this. Or you can say that the first derivative of this function is nothing but this. On the other hand, we can just compute this, because we are using the fact that the restricted root decomposition is orthogonal decomposition with respect to B. So if you use this fact, you can easily derive this. Therefore, we have this formula. Right. As a concrete example, if your regroup G is given by PSL NR, and if I choose our invariant symmetric bilinear form as a trace form, and if you use this particular invariant function, then the Goldman function is given by this. So if you replace 1 and 2 by I and I plus 1, we have zeros and 1 in the i's position and minus 1 in the I plus 1 position. And you can observe that the Cartan subalgebra of PSL NR can be written as an element of those forms like 1 minus 1 or 0, 1 minus 1, something like this. So we have the following. So we choose a Q when you define the Goldman flow, and you choose a essential simple closed curve gamma. We choose these two when you define the Goldman flow. And then the Goldman flow is the Hamiltonian flow for the following Hamiltonian function, where this f of gamma is here, and f is defined as follows. So this is a Q star, where Q star is a dual of Q, and this is an element of Cartan subalgebra, and lambda was the Jordan projection. So this is the theorem of Goldman, and that is to say, this means that the Hamiltonian, this is a definition of Hamiltonian flows, and the Hamiltonian, this being a Hamiltonian function means that if you evaluate your Atiyah-Bott-Goldman symplectic form, contract with the Hamiltonian vector field, we have the d of f of gamma. This is what I mean by f is the Hamiltonian function of your Goldman flow. Okay. Any questions so far? How many time? Yeah. Couple of minutes. Can quickly. F doesn't depend. I'm sorry, F hat. It does depend on x, but it is constant value. It has a constant value on the Weyl chamber, positive Weyl chamber. If you use if x is not in the positive Weyl chamber, we have to conjugate it, and the value is just conjugated. So it's not a constant function, but it is constant on the positive Weyl chamber. So some lemmas. Well, Goldman flows preserve Atiyah-Bott-Goldman form. Of course, this is not a property of Goldman flow, but the general property of Hamiltonian flows. And this is really a kind of special properties of Goldman flows. It's not necessarily true for general Hamiltonian flows, which says that, so if you are given a compact subset in your Hitchin component, and there is a constant depending on your compact set, such that if T is bigger than this particular constant, then we have n flown by Goldman flow for time t is always disjoint from the original set n. So this basically tells you that your Goldman flow is proper. I think I don't have enough time to prove everything, so let's just skip this proof. Just let me tell you some kind of ideas. We just lift our Goldman flow, Hitchin component to the Hitchin representation by using very special preferred section. And this section is kind of equivalent with respect to the Goldman flow. And therefore we can, enough to show this proposition for this lifted n and the lifted Goldman flows. And if you lift your Goldman flows, this action is very simple. It's just nothing but the conjugation on one side and multiplication on the new generator. So these two, the proof actually depends on whether your gamma is separating or non-separating. If your gamma is separating, your Goldman flow, what Goldman flow does is just take the conjugation on one side, and this conjugation action is actually proper if your representation is in the Hitchin. So that's why we have properness. And if your gamma is non-separating, you just multiply exponential minus T of Q on this new generator, and this action is also proper if you begin with the Hitchin representation. So that's actually indeed the proof of this proposition. Okay. And now we come to the Goldman product formula, which I'm going to use it tomorrow. So which tells you that how we compute the Atiyah-Bott-Goldman product between two Hamiltonian flows. So let's say f and g are invariant functions and choose two elements x and y as essential simple closed curves. Then you can define the Goldman flows associated to fg and x and y. And let's say f of x and xg of y are associated Hamiltonian vectors. If you compute the Atiyah-Bott-Goldman product between these two vectors at element rho, then you can compute it as the sum of this gadget, and the sum is taken over all the intersection point of x and y. So basically this x of p and y of p, we just choose x and y as an essential simple closed curve, and we make them as a fundamental group element by taking the base point p at the intersection point. So common base point p, it's the intersection point. Then it becomes a fundamental group element, and we evaluate it. And then you can evaluate it as by this representation. And that's it. And then you take this Goldman Goldman function of them, and they becomes an element in the real algebra. And then we take the product by B and take the sign and then sum. That's the formula. In particular, if X and Y are disjoint or the same curve, then we don't have this term. So the associated Hamiltonian vectors are commutative. And associated Hamiltonian flows also commute to each other. This property will be kind of used in tomorrow's talk. Okay, I think I'm running out of time, so let's stop here. Thank you.